Okay guys, let's go ahead and get started. This is part 2 of our series on limit definition of derivative. In the first video we talked about or reviewed sort of the conceptual backdrop and how we go from an understanding of slope on linears to average slope on curves, and how that tells us on a small enough interval about approximate slope on curves, and how we can use the limit process to go from approximate rates of change, approximate slopes, to exact slopes, or what are usually referred to once we go a little bit farther as instantaneous rates of change. But I'm going to go ahead and we're going to do a couple of functions here and run them through the limit definition of a derivative. And I'm going to try to focus at least the first 3 or 4 on ones that are very, very similar to the different varieties of limits that we had to evaluate using our analytic tools, okay? And that'll sort of tie this section together with that previous section. So let's go ahead and let's talk about, we talked about f of x is equal to x squared. Let's do another one of that variety. Let's do x cubed. It's a little bit more robust. It'll take a little bit more time. But if you remember binomial expansion, it shouldn't really be all that difficult. Okay, so f of x plus h winds up being x plus h cubed. And I know that the derivative should be the limit as h approaches 0 of, using f of x plus h and f of x plus h minus f of x, all of that over h. Okay, now obviously again, if I plug in 0 for h, and like I said, when you're not in this context, anytime that you're given a limit, the first thing you should try to do is plug in. But here, if I plug in, I get the indeterminate form. So I need to go ahead and I need to expand that binomial cubed. And if I remember Pascal's triangle, which I do, and I hope you do too, you wind up getting, remember 1, 3, 3, 1, 1, 3, 3, 1. Okay, sorry, my knuckle was in the way. 1, 3, 3, 1. And of course, from here, I notice, just like when I did the x squared, that leading term cancels out with the one that you're subtracting. Okay, and so I get the limit as x approaches 0. Now this is going to happen with every one that you do like this, that's of a polynomial variety. You're going to, once this and this cancel out, you're going to get a common factor of h up here in the remaining terms. That's kind of the point, okay? So if I were to factor out the h and go ahead and move it to here, I notice that the moment that I cancel those h's out and I plug, now I can actually plug in, right? I've changed the form, and you're changing the form so that you can evaluate by plugging in. Let's go ahead and plug in, and I'm going to get 3x squared, okay? Now, what if I have something like that we did in the Wolfram demonstration? That's f of x is equal to root x, okay? Now I'm looking for the derivative, which means I'm looking for the function which will describe the slope of f of x at any particular x. And I probably should have used g of x, but I sort of moved the previous problem out of the way, so I don't think it really matters. And we have f of x plus h. Now I know that the derivative, just like last time and just like always, is going to be the limit as h approaches 0, as h approaches 0 of f of x plus h minus f of x, all of that over h. Now, what strategy do we employ here? Well, it's obvious that we're going to be multiplying by the conjugate, okay? Okay, so when we multiply by the conjugate, and of course using the conjugate is employing the logic of the difference of two squares. So I don't even have to actually do the work in terms of getting what that numerator is going to be. I know what it's going to be. That's why I strategically employed that particular method, right? Now remember, the hard part about multiplying by the conjugate is you're so worried about getting the numerator correct, you'll forget to take this denominator and stick it here and carry it to the next step. Very, very important, okay? Now I notice that when I simplify that numerator, I'm going to wind up getting that. And of course, the h's will cancel. And remember, when I plug in the 0, those aren't multiplied together, those are added together. And so when I get two of the same thing, I'm going to get 1 over root x plus root x, or 1 over 2 root x. That is the derivative of that function. This function will describe the slope of that function. Remember, because all these equal signs mean that that's f prime. That's the derivative of f of x. This will describe the slope of that at any value of x. Okay? So that was, this one, the first example was multiplying it all out in order to simplify and evaluate the limit. The second one was multiplying by the conjugate. Well, let's go ahead and do an easy example of complex fractions. Okay? F of x is equal to 1 over x. Well, f of x plus h is equal to 1 over x plus h. So we know that the derivative, if we're arriving at it by limit definition, is that. And all of a sudden, there's our old friend, the limit of a complex fraction. Well, how do we take the limit of a complex fraction? Well, we uncomplexify it, right? We get rid of the complex nature of the fraction. And in order to simplify this fraction, you could, as I've said before, get a common denominator in that big numerator. But that's not the easiest way to do it. The easiest way to do it is determine what that common denominator would have been had you done it that way, and to multiply through by it. Or to put it another way, what's the problem here? The problem is divided by x plus h. Okay, well, if the problem is divided by x plus h, how do I undo that problem? Well, I multiply by x plus h, but I have to do it in the numerator and denominator, or I've changed the value. Okay, my second problem is x. Divided by x is a problem. That's what creates the complex nature of that fraction. So if divided by x is my problem, my solution, or my way of undoing that, is of course to multiply by x. And in doing so, you'll notice that this right here is the common denominator of that numerator over itself. That right here, this quantity, is 1. Therefore, I am allowed to multiply by it because I'm merely changing the form and not changing the value. So when I take this quantity and I distribute it to both of those fractions in the numerator, what I'm going to get is, when I distribute it to the first one, the x plus h's will cancel, and I'm left with x. When I distribute it to the second one, the x's will cancel, and I'll be left with x plus h. And what I have here is h, x plus h. Now, it's not usually as problematic forgetting that denominator and forgetting to join it up when you're doing complex fractions, because they're a little bit easier than multiplying by the conjugate. For some odd reason, people just get all weirded out when there are radicals around. But it is something that does occasionally happen, so please try and be wary of that, okay? So I have the limit as h approaches 0. Well, when I distribute that negative across that binomial right here, it's going to get x minus h. Well, the x's cancel out, and I'm left with minus h. Okay? Well, those h's obviously cancel out, and I'm left with negative 1 in the numerator. And I know that that means that I have the limit as h approaches 0 of negative 1 over x plus h. I now have changed the limit into a form so I can now plug in that 0 for the h. And what I get is negative 1 over x squared. And that is the derivative of the original. That is the derivative of that, okay? Now, let's go ahead and do one of those combination ones. Because it actually does occur, let's go ahead and do f of x is equal to 1 over root x. That's what I meant by combination. Because what happens is when we start doing the limit definition of the derivative, it winds up being both radical and complex fraction in its makeup, and therefore we have to employ both the conjugate and the undoing of a complex fraction in order to evaluate and get down to the derivative function, okay? And if you go back, if you don't remember doing that, we actually did maybe one or two like that in the evaluation of limits by analytic processes or by algebraic processes a couple videos ago. Now, the question is, I have two problems. Well, I mean, not just, 1, 2, but I have two major problems. One, the radicals. Two, the complex nature of the fraction, okay? Let's get rid of the complex nature of the fraction first. Let's simplify the complex fraction. Now, I know that I'm going to multiply by what would have been the common denominator. That shouldn't be a surprise. We just got done doing that in the last example. And so I have the limit as h approaches 0. When I distribute this to the first term, the radical x plus h cancels, and I'm left with radical x. Okay, when I do it to the second term, the rad x cancels, and I'm left with rad x plus h. Now again, make sure that you take this and join it up with the h as part of that new denominator. Okay, we don't want to leave things behind. That kind of screws up our answer. Now what I need to do from here is I now, because it's still indeterminate, right? You still have that h down here. You're still going to get 0 up in the numerator if I were to plug in. I need to free that x up in order to be able to cancel with that one, and that's what's going to get rid of the indeterminate form. So now, and this is going to make this denominator really messy, but you got to do it, right? Isn't it nice that we don't have to do it by limits forever, right? So we have the limit as h approaches 0 of x minus x plus h. And here we have a really nasty denominator, right? And just be very careful to use your brackets to take that functional binomial and plop it into the denominator. Now, I'm going to do a couple steps in one because I really don't want to rewrite all of this. This is going to simplify into negative h when I distribute the negative. Then I can cancel out with that h in the denominator and just be left with a negative 1 in the numerator. So I did two levels of simplification. One was addition-subtraction simplification in the numerator after distributing the negative, and the second one was canceling of factors from the numerator and denominator, namely the h. Okay, I hope everyone stayed with me on that one. Now it's in a form that I can go ahead and plug in. And I can go ahead and plug in, and I'm going to get root x, root x, root x plus root x. Okay? All I did was plug in a 0 for the h, and I didn't skip steps because I wanted everybody to see that. That's going to be negative 1 over x, 2 root x, or negative 1 over 2x to the 3/2. Okay? That, I know that was just nasty stuff right there. That is your derivative of that. Okay? So, we've done a couple of examples. We did examples that I think covered, if not all, at least most of the techniques that we had to deal with in the evaluation of limits analytically a few sections ago. From here, I'm going to get into some more, and these were, of course, all rudimentary ones, very, very plain. Notice that I didn't add anything to that. That was just very, very straightforward. Notice that I didn't add anything to that. It was just very, very straightforward. In the next lecture, what we're going to do is we're going to, of course, start adding stuff and maybe even get to one or two of the trig ones. So go ahead and stay tuned for that. and I'll get on that in just a second. See ya.